Okay, let's jump right in with a big question, one that seems like it should have a really simple, straightforward answer. But as you're about to see, things get a whole lot weirder. The question is, does gravity always slow down time?
So, this is the rule most of us learn, right? It's one of the big takeaways from Einstein's theory of general relativity. And it feels intuitive. The closer you are to something really massive, the stronger its gravity, and the more that gravity warps spacetime. So a clock down in that gravity well is going to tick slower than a clock way up high. Simple enough.
And this isn't just some abstract idea. It's real, and it's measurable. Get this. Because of the intense gravity at the center of our planet, the Earth's core is actually about 2.5 years younger than its surface. Wow. So far, that simple rule is looking pretty rock solid.
But how did we first prove this? To see that, we've got to go back to 1971 for what has to be one of the coolest and most direct tests of relativity ever dreamed up, the Hafele-Keating experiment.
The whole setup was just beautiful in its simplicity. Scientists took a bunch of super-duper accurate atomic clocks, put them on regular commercial airplanes, and just flew them around the world. One set went eastward, which is with the Earth's rotation, and the other set went westward against it. And all the while they had another set of clocks that just stayed put on the ground to use as a baseline. Okay, now this is where it gets really clever, because the scientists had to deal with two different effects from relativity that were fighting each other. First, you've got time dilation from speed, that special relativity. The faster you move, the slower time ticks for you. The plane flying east was moving fastest. But then you've got time dilation from gravity, that's general relativity. The planes were flying high up, where gravity is weaker, which means their clocks should have actually ticked faster than the ones on the ground. So you've got this cosmic tug-of-war. Speed says slow down, altitude says speed up. Who's going to win?
And check out the results. They were just spectacular. For the eastward trip, the speed effect went out, just like they thought, and the clocks actually lost about 59 nanoseconds. But for the westward trip, the effects added up, and the clocks gained about 273 nanoseconds. And the critical part? Look how close the measured numbers are to what the theories predicted. It's a slam dunk. Our simple rule seems absolutely unshakable.
But what if I told you it's not? What if I told you that under certain conditions, weird conditions for sure, but totally possible according to physics, that simple rule just completely falls apart? This is where our story takes a really fascinating turn.
The whole problem, the little crack in the foundation, comes from a deceptively simple question. What do we even mean by stronger gravity? You'd think that's obvious, but in the world of general relativity, it's actually kind of slippery.
See, there are really two ways you can think about it. One way is observer independent. It's just a property of the universe. Gravity is the actual curvature of space-time, something you could measure with a scalar. It's there whether you're around to feel it or not. But then there's the other way, the observer-dependent view. This is gravity as a force you feel, the force you have to physically resist to keep from falling. In physics, we call this your acceleration. And believe it or not, this one little distinction changes everything.
Okay, one last key concept before we get to the big reveal. We need to understand what a stationary observer is. Now, this doesn't just mean someone standing still. In relativity, it's an observer maintaining a perfectly constant state of motion in a gravity field. So, someone hovering at a fixed altitude above a planet, or, and this is the important one, someone in a perfectly stable, circular orbit.
All right, we have all our pieces on the board. Let's look at the scenario that flips our nice, simple rule completely on its head. Let's picture a bunch of observers, each in their own perfectly circular, stable orbit around something incredibly massive, say a black hole. They're all stationary observers by our new definition, each one just cruising along in their orbit.
And here it is, the mind bender. It turns out that in certain stable orbits, the clocks for the observers who are farther away from the black hole actually run slower than the clocks for observers who are closer. Let that sink in. Farther away, where gravity is weaker, time is passing more slowly. Wait, what? That is the exact opposite of everything we've established. How is that even possible?
The solution to this paradox, it turns out, isn't really about gravity at all. It's about the other definition we talked about, the force you feel to stay on your path.
So think about it like this. You're swinging a ball on a string. The farther out the ball is, the harder you have to pull on that string to keep it whipping around in a circle, right? Well, in these very specific distant orbits, the centripetal force you need to stay in that circular path is actually stronger than the force of gravity pulling you in. So the total force that observer is feeling,
Their force acceleration isn't them pushing out against gravity. It's actually a constant pull inward, just like the tension on that string that's required to keep them on that wide circular track. And the direction of that felt force is the key.
This leads us to a new, more precise, and frankly, more powerful rule. Time slows down for a stationary observer in the direction opposite to their forward acceleration. Let's trace that. For us on Earth, our acceleration is upward, pushing against gravity. So time slows down in the opposite direction, downward, toward the core. That fits. But for our special orbiting observer, their net acceleration is inward, to stay in orbit. So time slows down in the opposite direction, outward, to the farther orbits. The paradox is solved. It's not about gravity's strength, it's about the direction of your acceleration.
If that still feels a little bit out there, here's a really simple analogy. Think of a spinning record. You have one dot near the center and one dot out at the edge. They both complete a full circle in the exact same amount of time. But the dot on the edge has to travel a much longer physical path to do it. This difference in their path through space is a perfect parallel for how different observers can have different paths through time, all depending on their acceleration.
Okay, so you might be thinking, that's a neat little puzzle, but it's a super specific scenario. Why does this nuance actually matter? Well, it matters because this is how science works, and it has some very real-world consequences.
So let's wrap up with the big takeaways. First, that simple rule that stronger gravity slows time. It's a great rule of thumb, but it's not the whole story. The deeper truth for a stationary observer is that acceleration is what's really in the driver's seat. And this process of finding a simple rule, then testing its limits, then finding a deeper, more accurate rule, that is the heart and soul of science. And it's not just an academic exercise.
In fact, you rely on this incredibly precise physics every single day. The GPS satellites orbiting Earth are experiencing both kinds of time dilation, just like those clocks on the planes. Their clocks naturally tick a little faster than ours down here. If the engineers didn't account for both of these relativistic effects with pinpoint accuracy, your GPS would be off by miles within a single day. The whole system would be totally useless.
So it kind of makes you wonder, doesn't it? The next time you hear a simple rule of science, it's worth asking, is that the whole story? What other elegant truths might be hiding an even deeper, more complex, and more fascinating reality just waiting to be discovered?